Welcome. Today, Professor Odersky, am I pronouncing that right?
Yeah.
Is here to speak to us about Scala and about future-proofing collections. So I don't want to waste any time on me. So.
Okay, thank you. Well, thanks for arranging this on short notice. I noticed that the screen is actually over here, so I guess your heads will go ping-pong from the speaker to the screen, but we'll make it work. Okay, so my talk is about future-proofing collections from mutable to persistent and parallel, and it's essentially a story of what the Scala collections have taken, the development of those collections. So I say a couple of words about Scala first. How many in this room actually have already written Scala code? Almost all of them. Very good. Didn't know it was so widely used in Google. Okay, but a little bit of history. So I believe it's now one of the main alternative languages on the JVM. The way it started was that very early in the 90s I got involved with Java. Actually, I got involved before Netscape got involved with Java. And the reason was that we found that would be probably a very cool platform for functional programming, because Java was the first mainstream platform that had a garbage collector. And at the time it was a really big thing. Today, of course, it's completely standard. So what we did was a language called Pizza that took some elements of functional programming, added those into Java, and that was a moderate success. But the big thing afterwards was that some people at Sun, namely Gila Brache and David Staudenmayer, came to us and said, look, what you did with Pizza, we don't care for higher order functions, we don't care for closures. Java still doesn't have closures, but it might acquire it soon, finally. We don't care for pattern matching, but the generic types that you have, that's interesting. And so we developed GJ, which was the predecessor of generic Java, and Java 5 that came out in 2003. And in the same course of action, Sun actually took over the Java C compiler that I wrote, which was the compiler for GJ, and made it their standard compiler. So that was all in the 90s. And in the last 10 years, when I joined EPFL, I thought I'd take a step back and said, well, what could we come up with if we are not backwards compatible constrained with Java? So if we could start from a clean sheet, and if the only requirement that we had was that we should be fully interoperable, but if we didn't need to have actually an extended syntax for these things. And that became Scala, and I think I gave a Google Tech talk about 2006, 2007, which was called the Scala Experiment. That was here in this building. And so that was sort of the end of the experimental phase. Over the last 3 years, we've been very busy essentially driving and supporting industrial adoption, because it actually turned out that the experiment worked pretty well. So here's, if you look at the current state of traction, then we have about 100,000 visitors a month on our website, 40,000 downloads a month. That represents a 5 times growth over last year. There's a steadily increasing stream of books out and more in the pipeline. We have many user groups, and we have about 60% of the traffic comes from the US, 30% Europe, and 10% rest of the world. And another nice thing is that we just got voted most popular non-Java language in an informal whiteboard poll at Devox, which is the biggest independent Java conference in Europe, which was out there a couple of weeks ago. Okay, so these are some of the companies that are using Scala. So it's a big list, growing, so it's not all of them. I think the important point there is that they're using Scala not as a side project of a single guy or something like that, but a lot of them are really using it for their backbone infrastructure. So for instance, if you look at Twitter, they started to migrate the core messaging service from Ruby to sustain a 3 orders of magnitude growth since 2008 when they switched them. And now essentially almost all the APIs, customer-facing APIs, are Scala APIs. LinkedIn, again, it was 2 years ago, it was two guys or something like that. Now it's, I think, 2 full groups with more than 20 developers doing full-time Scala. Among others, it drives their social graph service with 380 to 400 million transactions per day. Foursquare, the startup, is the entire website and all services written in Scala. So they had a big outage recently. You might have heard about it. And I'm very glad, relieved from my side, that the outage was due to MongoDB and not to Scala. So Scala was worked well for them, it was another reason. So all these are web companies, and that's certainly a big adoption vector. Another one which is very strong now and growing stronger is in finance. So, for instance, EDF, it's the EU's largest energy firm. They make right to 300K lines of contract modeling code from Java to Scala. And another interesting thing is that UBS, one of the 10 world's 10 biggest banks, just approved Scala for general production usage. And if you know banks, you know that this is actually a very, very big step for a bank to do that. And there are lots of others as well. So if you want to more stories, we can take them to the question time. So why Scala? What do these companies find in Scala? So I think the most important slide, if I had only one slide, it would be this one, to say, well, what Scala really is, it's a unifier. And it's a unifier in two dimensions. In the vertical axis here, you say, well, it's on the one hand, it's almost a scripting language. In fact, it's so much a scripting language that we got invited for the third year running to the Java 1 Script Bowl, which is essentially a popularity contest for scripting languages. So there we go up against Groovy and JRuby and other scripting languages on the JVM. On the other hand, you could say, well, nothing's further from the truth that this is a scripting language because it has a very, very strong type system and it has a very performant runtime. So it's really a workhorse language, just like Java. It's only more so because the type system actually lets you compose things in more interesting ways, in more robust ways than what Java lets you do. So it's a big change from a scripting language program where you maybe have one line of code, 10 lines of code, to a workhorse systems language where you have hundreds of thousands of lines of code. And how can we do that with one language, both of these extremes? So I think the secret sauce is that Scala tries, like no other language, really to be a fusion of functional and object-oriented languages, functional and object-oriented programming concepts. So what I mean by that is not having two concepts side by side, but really try to unify those concepts in interesting ways. For instance, functions in Scala are objects. They're one and the same thing. Okay, so let's see an example, enough talk here. So that's, of course, a class. You can all read that. I assume you all know Java. So class of persons. But if you look at it and you don't, let's say you don't know Java by heart, and you say, well, this looks strange because everything is repeated 3 times. There are 3 names, there are 3 ages in here. Why do people stutter so much? So here's the same class in Scala. You see the repetition is gone, so everything is mentioned once. It means more or less exactly the same thing. So you have a class of persons. It takes 2 parameters which you pass directly to the class, a name and an age. And the val in front of the name and the age, the val here, that tells you that it's actually a field of the same class with the same name. Josh?
So any reason the constructor is package private in the Java version?
No, it should be public. You're right. Yeah. Good point. Yeah. Okay, and so the val means it's a field, and the field, furthermore, it means that the field is immutable, which, since Scala has a strong functional tradition, is the recommended way to write fields, unless you have a good reason to make them mutable. If they should be mutable, you just write var instead of val, and that would give you a mutable field. Okay, you might say, big deal. If I use Eclipse, then that code will be written for me, so that's not a big savings. And that might be true, but let's have a usage of this. Have a look at the usage of this class. So what does this thing do here? It's not so hard. So it seems to split an array of people into an array of minors and an array of adults, right? And I was a bit mean that I specified arrays as the input-output data structure because they are very rigid type. You can't let them grow as you need to. So internally it goes over array lists, and then in the end it puts these things back into arrays. So that's the same thing written in Scala. So you have the array of people, and then you say minus adults equals people partition with age less than 18. So I think there's no contest to say which of these solutions is clearer. And even if you're used to reading Java code, I think still you would concede that the version down here is way clearer and easier to read. And it's also, it turns out, much easier to get right, or otherwise put, if you don't get it right, you have a much higher chance that the type checker will actually catch you out than in the Java version up here. So it's more robust. So this thing here shows, in a nutshell, 3 of the important concepts that Scala has over Java. The first thing is here on the left-hand side of the assignment, you see that actually there are 2 variables being defined, minors and adults. So that's a very simple example of a pattern match, which we support in Scala. That's what was one of the things that the Sun people at the time didn't want at all coming from pizza. So the next thing you see here is the partition operator. That's actually just an infix method call. So it's a call. It's an invocation of a method on the people array. You might say, well, wait a minute, what kind of array is this? And in fact, it's exactly the same array that you have in Java. There's no wrapping going on. So you might say, well, last time I saw arrays didn't have a partition method. And that's true. So there's some serious magic, not in the compiler, but in the libraries, to actually inject these methods with so-called implicits, or there's a so-called pattern called pip my library, which is very common in Java in Scala programs. And the last element here, well, that's our closure, a function value, a very simple form of one, where you say, okay, you have a parameter, and that is signified by the underscore here, and you take the age value of the parameter, which is a person, and you compare with 18. So that's the function that you pass into the partition method. And the type of the parameter, signified by the underscore, that's invert, because Scala has a pretty powerful type inferencer, so you don't need to write the type of these closures as a general rule. Okay, so the bottom line of that is that if you go from Java to Scala, you can expect at least a factor of 2 reduction in lines of code. And I'm really being conservative here. So to just take one witness, Guy Steele, they ported the Fortress compiler from Java to Scala. They reported a 4 times reduction of lines of code. And that's somebody who's actually employed by Sun or Oracle now. So I think factor of 2 is really something you can always expect. Yes?
So I believe your factor of 2. I should point out that if Guy ported it from Java to Java, he would have gotten a factor of 2 there as well.
Okay, but he got a factor of 4. So
yeah, understood. There's your factor of 2.
Good, important. Okay, so, but the other possible objection is, well, does that really matter? Doesn't Eclipse write these extra lines for me? And I think the correct answer to that is, well, maybe sometimes not. But it certainly won't read those extra lines for you. And after all, we know that reading is more important than writing software, at least should be. So the question is now, reading, can we read those half the lines faster? And that we actually did an experiment on that. So we set a bunch of subjects in front of a computer screen and asked them to understand 2 versions of the same library code. That was, I think, some relational algebra routines. And one half of the sample was written in a way you would write it in Java. It was both Scala to keep the language constant, but one way was written in the same way you would have written it in Java, which you can do in Scala, of course, and the other was written in a way which made use of the functional capabilities of Scala. And what we found out in this experiment is that the average time spent per word of source code, per token, was constant for the program understanding. So that means fewer words, indeed, faster understanding. It doesn't mean that the fastest language to understand is APL, because while in APL programs are very, very short, every token is a single character. So it's per word of source code, not per character, that this relationship was established. Okay, you might say, well, that's very good, and okay, I believe it's a more concise, maybe more productive Java, but actually, if it stopped there, that wouldn't be half of the story, because there's much more to it, and the more to it has all to do with domain-specific languages. So Scala is really good at embedding a lot of domain-specific languages that just then take the form of high-level libraries, high-level APIs. So just as a single example, you see here on the right the actors abstractions that are used in in the Scala actors library and that are in similar form in the akka version for distributed actors. So actors we shamelessly stole from Erlang. Erlang has used actors for 20 years, very successfully in telecoms and now internet systems. So the idea of actors is very simple. You have an asynchronous message send expressed, you write actor bang message, so you send this message to the actor. And then on the other side, the actor can decide when they want to receive messages and what kind of messages they want to handle at any one point. So that's expressed with this receive method, which takes a bunch of pattern matches, so it takes a bunch of message patterns and associated actions. And the idea is that it would scan the inbox of messages that are pending, and if any message matches one of these patterns, it will pick the first of those messages, execute the corresponding action. And if no message matches, then it would just suspend and wait for further messages. Okay, so the point in this example is you might think that this is something that's in Scala, the language, but that's actually not true. Scala doesn't have any concurrency primitives, except that it works with standard Java threads and it has synchronized just as Java has synchronized. So all these things are constructs that are written as methods. So for instance, the bang, well, that's just another infix method that happens to be called bang. And the receive here, it's a more evolved thing. It's a higher order method that takes another function value, which is this pattern matching expression. So that's just one example that demonstrates how one can really organically grow the language into completely new directions and do so in a way which makes it not look like something that is strange and more difficult to use than the base language. It looks completely organic. And it has been done in many, many different instances. So akka actors are one example, so that they're used in akka, Twitter's message queues, and so on. There are lots and lots of really nice testing frameworks. Specs and Scala Check are just two examples. There are lots of very interesting database mappers like Scala Query, Querylers from Twitter, and so on. So all these things is essentially there's a whole ecosystem of doing embedded languages on top of Scala as the base language. Now, that was sort of a quick introduction what Scala is. And since we had concurrency, I've now come to essentially why concurrency is interesting and how we took this further. So of course concurrency is interesting because we have a big context shift now. The speed of processors isn't increasing anymore. Already since 5 years it has remained largely constant. So what we get instead for increasing transistor budgets is more cores. And that basic fact, everybody knows about it, but it has been ignored in everyday programming to a large degree. I mean, what people do is they say, well, on servers, the thing is simple. I just distribute my users over more cores, and that's true. On clients, well, I might get faster graphics because I know how to parallelize that. And for the rest, well, these cores are mostly idle. And maybe that's defensible if you have 2 cores or 4 cores. But what if you had like 24,000 parallel threads? So this processor here, that's an NVIDIA Fermi, that will to keep that fully busy, you need 24,000 running threads. Otherwise, it would just not be fully loaded. So that's now being really a big problem. I mean, how people are going to find all these parallel threads and how are they going to organize them? So that has been called the PPP Grand Challenge by the computer architecture community. So PPP is short for Popular Parallel Programming. And essentially it means that the computer architecture people, they throw all these chips on our site and says, well, you figure out how to program them. We call it a Grand Challenge, and that's our contribution to the whole thing. Okay, so how do we do that? Well, one thing that you often hear today is concurrent programming. So because of parallelism, suddenly Erlang has got a renaissance, and all these fancy things like actors with messages, agents, STM, they're gonna save the day. And I believe all these concepts are really useful. I mean, they're the right abstractions, and they're much better than threads and blocks, no doubt about it. But by themselves, they won't solve this PPP challenge, simply because no matter how you do it, you will always have a hard time doing concurrent programming. Because there's this fundamental problem of non-determinism. So Whenever you have a program which is non-deterministic, it's just painful. You can have Heisenbergs, you have different behavior on different hardwares. I had crashes on Macs that weren't reproducible on Windows, and so on and so on. It's just painful. So what do you do there? Well, the root of the problem is non-determinism. So concurrent threads accessing shared mutable state are inherently non-deterministic. So in this simple example here on the right, you have just two asynchronous computations, a shared mutable variable, and that can give you 0, 1, or 2. And even if you say, well, the asyncs are in fact atomic, so you will not actually have any interleaving between these blocks, it's still non-deterministic because one can run before the other. So you don't have an order of these two things. Okay, so if non-determinism arises almost inevitably from parallel processing in mutable state, and we say we can't do without parallel processing because, well, hardware forces us to do parallel processing, then it's axiomatic that we have to eliminate or, let's say, reduce mutable state, because, I mean, otherwise we will just run into this problem head on. There is no other solution. So to get to deterministic processing, minimize the mutable state. And avoiding mutable state means programming functionally. So that's essentially the secret of saying, well, essentially, if you want to deal with that, that's why functional programming has this sort of renaissance to say, well, it addresses this problem. So another way to look at that, and that's a little bit philosophical, is to say, well, if you program functional, it's really a completely different mindset from programming imperatively. So if you program imperatively, you program in time. You think about, well, first I do, the computer does this, and then it does that, and then this other thing happens. So it's really, you align things on a time axis. In functional programming, you're not concerned with time at all. It doesn't matter when these things run. What you're concerned with is what do you construct, and out of what other things you construct this thing. So the mental model is much more a space-oriented model that you say, well, I construct this interesting thing from that, and then this other thing, and so on. It has to be experienced to really sink in, but that's really what it is. So if you look at that now to say, well, if I go in space, then I can have lots of parallel computations that essentially build different parts of the same thing. It's it's no problem there. So for instance, if I build a cathedral, then I can build a cathedral with many, many different workers, and they all would build a different part, and at the end, I have a cathedral. On the other hand, if I go in time, then, well, I have this one thread, and I have the second thread, and then I have a third thread, and a fourth thread, and the more threads I have, the more fiddly it becomes, because they might actually want to access the same things at the same time. I have these races, I might have deadlocks and so on. So that's sort of a very rough approximation, but I think one which is fundamentally true to say why functional programming is really the right way to do things here. Okay, so what does it all have to do with collections? Well, collections essentially build interesting things in space. If you want to build something which is just not more than just a single value or a single class that you've defined, you will inevitably have something like collections. And I give you a quick way to show you how Scala deals with collections. So in fact, Scala, like as often, it doesn't really take a single stand. It says, well, if you want mutable collections, we have those, and you can program them in pretty much the same way as in Java. But there's also a different set of immutable collections where destructive updates are not possible. So, and generally, these immutable collections, they're more popular, they're default in Scala programs. So that means we de-emphasize destructive updates, and instead of having this CRUD thing, create, read, update, delete in collections, we essentially have collection transformers. We create new collections out of old collections. That's the functional way. And to make that efficient, we have a complete range of persistent collections. So for instance, what you do here is you have a list, and then you map a function over the list that gives you a new list, and so on. So the collection properties that we have is that they're object-oriented, so they are fit into a natural hierarchy. You're going to see a bit more of the hierarchy later on. They're generic, of course, so it's list of t, of some element type t, or map of key value. They're optionally persistent, so all collections in the immutable package are persistent, and they're higher order, so typical methods you deal with collections are things like for each, map, filter. And the last one seems kind of natural, but it's actually very hard to achieve, is what we call the uniform return type principle. And that's that operations should return collections of the same type as the operand they work on. So if you, let's say, do a map over a set, you get back a set. If you do a map over a list, you get back a list. If you do a map over a vector, you get back a vector. So not just a standard result type, but you always map back into the same type. And that actually turns out to make a very elegant and powerful combination. So I quickly run you down to some of the basic things, and then I want to do one concrete coding thing, because here at Google, I mean, code is king, code is what matters, so I do a little bit of live coding here. Okay, so the collections, so what you have is you can build a constructor collection like that. List 1, 2, 3, list is the name of the collection here, and the Scala, so what I do here is I simulate the Scala interpreter, the Scala reference. So that would then be the answer what the Scala interpreter throws back at me. So then I can map that by incrementing every value in the list. So it would give me back the list 2, 3, 4. Then that's another way to write the incrementation, only shorter. I can also have a filter, which says, well, now I want to get all the elements that are even in the list. So that gives me that. And here's another one, which is a bit more involved, that I have another form of creating special kind of collections called ranges with the to method on integers. So 0, 2, this parameter, which would give me a range from 0 to whatever the parameter was. So if I do that, then I get a list of 3 ranges, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4. Okay. Other operations I have is I have an operation flatten that takes a list of other collections and just concatenates all the elements. So doing that on the last list would give me this longer list. And I can actually join the map and the flatten to a flat map. So flat map just takes a function that returns a collection, in this case this thing here, and it would just apply the function to each element in the list, concatenate all the results. So that's a flat map here. Gives me the same thing as map and flatten. Okay, and the last one is group by, which is also a nice operation that if you work with databases, you know that. So group by goes from takes a collection, in this case, to change things a little bit, I gave you a vector, not a list. And the group by now gives you a map by that's constructed. So essentially, you have a function here. In this case, head takes the first character of every element here, and just take this here. Okay, so that gives you that, and then it would just map back. It would say, well, from the A I get the apple, and from the P I get pear and pineapple. So essentially, I take the function and then generate a map that maps back into a subcollection. That's a standard function that you know in SQL, say group by does the same thing. Okay, so that's one side of collections. The other side is for notation. So for notation is a very convenient way to essentially write certain collection operations. So the first one, for instance, is this here. So it looks like a for loop, but it ends in yield, and it always gives you back a new value, so for every element. So for instance, this one here is the same as map. It would just add 1 to each element and return the list. This one here is the same as filter. So you would take a collection, you would have an if, and you would then yield the thing. And finally, this one here, which has 2 generators, an XS, and the range. So that's the same as flat map. So you go through XS, you go through the range, and every element you pull out of the range, you return from the list. Okay, so that was the primer that I have to introduce so that you can now all follow so I need one more, namely using maps. We don't have maps yet. So maps are written like that. So you start with the name of what you want, map. If you want to be more specific, you would say hash map or tree map. And then you give a lot of associations, bindings from keys to values in this form here. So 1 maps to ABC, 2 maps to DEF, 3 maps to GHI. I should say, again, none of this is syntax, so Scala has no idea of what a collection literal is or what a binding is. So all of that is libraries. So basically the right arrow is a method that can be injected on any object in Scala, and it will just return a pair of its left operand and its right operand. So that's how you construct these. Okay, so that gives you a map of whatever you've written. So now you can select in the map, and that gives you the string that corresponds to the number 2. You can also add new bindings to the map with plus. So it gives you the map that just has this new binding. So none of this changes the map. They all generate new maps out of old ones. And you can also, for instance, apply a function to the map. So this function here just changes the keys into values. So now you get a map that goes from strings to digits in the other way around.
Martin?
Yeah.
M plus creates a new map, doesn't modify.
Creates a new map, that's right. If you want a modified map, you write plus equals. M plus equals would be could be applied only to a mutable map, and it would do the update in place. It's a systematic convention that whenever you have an update, the operator ends with an equals. Okay. So now I want to take you through a little example, and the example is interesting because it's actually been done before in a systematic study of essentially programmer productivity and programming language, productivity and efficiency. So the task is to invent mnemonics, phrases, catchphrases for telephone numbers. So for instance, something that you've given a number and then you want to find a phrase, something like 1-800-CALL-ME or something like that, right? So find a phrase that matches your telephone number. So for instance, if you had this number here, then you should have as one of the possible phrases Scala rocks. Because 7 contains the letter S, 2 contains the letter C, and 2 also contains the letter A, and so on. So you find this phrase. So what you want to do is you're given a dictionary as a list of words. And you want to design a class coder with a method translate, such that new coder of dictionary translate phone number gives you all phrases that match to this phone number. So coder dictionary gives you the class, and then you invoke translate invoke the translate method with a phone number, and you should get back then for each time all the phrases. So that example was taken from a paper called An Empirical Comparison of 7 Programming Languages. It appeared in IEEE Computer already 10 years ago, but it actually turns out because these studies are rather expensive, there are very, very few of them. So actually that's still the last one of general programming language comparison that I've seen. At the time, they tested it with Tcl, Python, Perl, Rex, Java, C++, and C. And then, of course, they asked interesting questions like which language yields the fastest programs? What do you think? Which one is fastest in all these languages? C?
Yes.
Tcl?
C++.
Are they actually apples to apples comparison? How do you, are they the same algorithm?
Every language had, I think, overall there were, I think, about 100 groups split over those languages, and they were free to pick any algorithm they would find. So it's really essentially what did people come up with. No algorithm was given.
So you're asking who the smartest programmers are.
In a sense, yeah, you could do that, yeah.
And it isn't clear that you have a statistical sample within each language, because 7 languages, 100 people. I mean, that's.
I think it was good enough. So they did it with statistic analysis, and I think it stood up reasonably well. So the answer is it actually depends what exactly you want to know. The fastest program was in C or C++, no doubt about it. The slowest program was also in C and C++. And it went further. So you said, well, what's the fastest average? And actually, the fastest average were the scripting languages. What's the fastest median? The fastest median were the standard languages like Java, C++, and C. So how that? Well, it actually turned out that the scripting languages all had standard collection libraries that were well known to programmers, that had good syntax for them. So people used them. And so they used pretty much standard pre-canned solutions, whereas people in C++, C, and at the time Java, didn't really have those languages, and libraries ought to know them sufficiently. So they wrote their own. And you can imagine that sometimes when you roll your own, you do a brilliant thing which beats the pre-canned solution by a wide margin. But imagine, let's say, doing collections, associative maps with linked lists, and I'm sure that programmers did that as well. So you add orders of magnitude factors to your performance, and those gave you really absolutely rotten solutions which ruined the average for the standard languages. More stable was the code size medians, which were about 100 lines for scripting languages, 200-300 lines of code for the others. So I'm going to do that now with Scala, and then we're going to do it together. So that's essentially the outline of our class Coda. So I've given you the mnemonics map, which says 2 is A, B, C, 3 is D, F. It's just what you have on the keyboard of your phone. And then I essentially have going to progress through 4 methods. The first says, well, I'm going to show you the methods one after the other afterwards. So the first method says, well, we want to invert the mnemonics map to give a map from characters A to Z to digits 2 to 9. Well, I could just write down the map. It's a finite map, but I'm lazy. I don't want to write down all these bindings. So let me quickly have a method, warm-up method, to just do that. So how do I do that? Well, here's how you would do it. You would just go through the map, mnemonics, and that would give you pairs of keys and values called digit, and the values is a string of letters. And then you go through that string. Every letter that you get gives you a new binding from that letter to digits. Right? That's really simple. So that's all you need to do for that. The next thing is word code. So that should map a word to the digit string it can represent. So not a single character, but a whole word. So what do you do then? So for instance, Java, you now want to map to the word 5282, because that's a digit string that represents the word Java. So that's what you do. You just have a map. Well, you notice that the car code only works for uppercase letters, so we want to convert the word first to uppercase. That's just the Java method. And then we just say, well, for each one of them, apply car code and give you the string. So one thing you notice here is strings are collections, and you have the uniform return type principle. So if you map a string, a character-to-character function over a string, you get back a string. So that's what it gives you. Third one, words for num. So it's a map from digit strings to the words that represent them. So what do you do there? So for instance, now you want to say, so the previous one said Java goes to 5282. Now we want to turn it around and say, what words does 5282 correspond to? And the answer will be a set Java, but also kata or lava. They're all mapped to 5282. And we want the set of all of them. So what do you do here? It's actually good to write down the type what you want. You want to map from string to list of strings. So here, this thing is actually represented as a list. Okay, so that actually takes some time to wrap your head around it, but if you look at it, it's just that. It's words grouped by word code. So it's a group by. It's nothing but that. So it's just group by is turning these things around. Okay, and now we come to the final method, and that will be not a one-liner, so it would be too simple. That's now the encode method. So we want to return all ways to encode a number as a list of words. So the signature is it takes a number, digit string, and it takes a list of words. That's a phrase. So every phrase is a list of strings. Every string is a word. And we want the set of all solutions. So not just one, but so the result type is set of list of string. Okay, so let's get started. So the first thing is to say, well, let's do the borderline case first. The number might be empty. In that case, there is a solution that corresponds to that. That's just the empty phrase. The empty phrase corresponds to the empty number. And our solution in that case is a set of an empty list, set of list of numbers. The next thing is to say, well, what are my choices? So the first choice I have is to say, well, how long is the first word in that phrase? Because the phrase might consist of more than one word. So the question is, how long will the first word be? So the possible choices are, it might be just a single character, or it might go up to the whole length of the number. So in that case, I would have a single word in my phrase. So I say, okay, let's go from 1 to the length of the number and convert this thing to a set. Okay, and now I do that thing with a for. I say, okay, let's take every one of those. Consider every one of those, call it my split point. What do I need to do now? I need to say, well, give me all words that correspond to the first digits that I've selected that way. First digits that I've selected that way, I can express as number, take, split point. Take is a method that works on all collections, including strings. I could also have written number, substring, 0, split point. It would have been the same thing. Then the next thing is to say, okay, now I have all the words that correspond to my first digit string. Now I have to still encode the rest of my phrase. So that would be number, drop, split point. And I do a recursive call to encode. And I let rest iterate over all of these things. And now finally to assemble my phrase, I say, well, I give you back the word, all possibilities for words that I have found here, and all possibilities for the rest of the phrases that I have found in this line. I compose them, so this double colon is a list cons operator into a new list. And that's it. So overall, this thing is maybe 20 or 25 lines. And I think it had to do with the fact, why could we get this much more concise and I would argue elegant program than the other solutions? And I think it really had to do to say, well, from C to Python and Teckle, the big thing why they were shorter was the introduction of collections. And here I think the big thing why we are still a lot shorter than that is the introduction of these functional collections that are these powerful operators that you transform one to the other. So this was a program that was pretty hard, and the groups needed, I think, an afternoon or something like that, and we just did it in 5 minutes or 10 minutes. Well, of course, it was rehearsed and everything. But, I mean, the general thing is once you get the hang of it, it's really very, very simple, and that's the beauty of it. This is not rocket science. It's extremely simple to come up with solutions using this powerful set of combinations. I have, for instance, I have given a lot of Scala courses recently to industrial programmers in 2-day courses and things like that. And the difficulty, of course, is always that they can wrap their head around this new thing, functional programming, because that's what they don't know. And my experience always was I teach them the basics, which is essentially pattern matching and recursion and all these things. And it's very, very hard. So they find that really hard because it's completely new to them, and recursion is difficult. We know it's difficult. Pattern matching is something new, and so on. And then the first time I did it, I said, oh, that didn't go too well. So now comes essentially the second level that I teach them these higher order operations. And I say, oh, I'm going to lose them all. But in fact, the opposite was true. They started to fly immediately with that. They got it immediately, and they could do the exercises very quickly, and they got it very quickly. And I was really surprised at that at first, and I met Butler Lampson afterwards, and I talked to him about it, and he said, no, he's not surprised at all. Actually, if we think back to our first loop, the first time we wrote a loop, that was very hard too. And the reason why it's hard is that there are many, many steps. Steps in time, recursion is also many, many steps, and actually controlling many steps is hard. Whereas these things, there are very, very few steps because every operation does a whole lot to your collections. So if you want to get to a fixed distance and you want to do it simply, then the best thing you can get there is you have very, very powerful operators that do a lot, because that means you need fewer steps to get there, fewer mental steps. And that's why the people actually the programmers found it actually rather nice and simple. The other thing that's really nice about this, that's a style of programming that gives you an extremely dense safety net for the type checker. That if anything goes wrong, your chances are overwhelming that the type checker will catch you out.
Is this more about the fact that it's functional, or more about the fact that you added those particular methods? I mean, could you do the same? Do you feel that you could do the same thing by adding a bunch of methods to the string class in Java that it groups, or to the set class?
Both. So they are very powerful methods, so you can't get them wrong anymore because they have been done for you. But the other importance is that since they are functional, essentially all the interactions of these methods with the context, with the rest, take the form of parameters or results. And all the parameters and results are subject to the type checker. Whereas
it's not. So I was thinking about, you can obviously write any function like that.
Yeah.
I guess the way I was thinking about, when you said functional, I was thinking about it as, it's more like a functional language, more like an ML or a Haskell or something like that. But that's not the thing you're trying to stress. The thing you're trying to stress is that there aren't any side effects and you don't have to worry about that sort of
Yeah.
thing. Okay.
And because there are no side effects, essentially, so for instance, you get the order of parameters wrong, something like that. Very likely, the type checker will catch you out. You get the order of 2 assignments wrong, no way the type checker will help you. It's just wrong, right? So you will find out at runtime. So that's why what I mean that the type checker really gives you a much denser safety net for this form of programming. Okay, so you might say, well, what does it all have to do with parallelism? And in fact, the beauty is that essentially we're almost there. So you see here 2 small things in red, and these 2, each of these essentially parallelizes 1/2 of the program. So the first one is to say, well, to actually generate this map worst for num in parallel, all I need to do is, I shouldn't pass in a list, that's an inherently sequential data structure, I pass in a parallel array. And once I do that, all these operations that I have, map, flat map, filter, or the 4 expressions that map into these operations, they would run in parallel. So there's nothing more you need to do. And the second part here is, when we actually do the encode thing, if you want to do that in parallel, then I could do it at any point here, but here I just say my split set, I want to turn that into a parallel set. So on sequential collections, you have this method par, which turns the same collection into a parallel collection. And then again, afterwards, all the operations that you have on this collection would work in parallel. Yeah?
This may sound flip, but if you've tested it, does it run faster in parallel?
This one here?
Yeah.
I haven't tested this one here because my dictionary is not fully enough. But
I have a 200,000 word dictionary I can send you.
Okay, cool. We'll test it.
You probably have to give them a pretty long string of numbers before it actually ran fast.
Oh, that was kind of my point.
But that's not the point.
Yeah. In general, if you have large data sets, yes, I mean, it parallelizes quite nicely. Okay, so that's a parallel collection, and that's a mapping from sequential collection parallel, and that's essentially all there is to it. So in summary, in the original experiment, the scripting languages were shorter and often faster because the developers tended to use standard collections. And in Scala solution, we obtained a further 5 times reduction in size through the use of functional collections, and they're easily translatable to parallel. So the advice I would give here is think collection transformers, not try. Yeah. Sure.
So part of the 5 times is it's just not fair to compare you to their group of programmers.
Also true, yeah. So you can, like you did with Fortress, you can deduct half of it and you still get to an.
Oh, let me try it in Java and we'll see how.
Okay.
See where I get.
That's fine. That will be a good comparison. Yeah, let's do that. Okay. Yeah.
So the par addition that you added to make it work in parallel now, is this telling the threading library to break these operations down into multiple threads, or is it just making it parallelizable and you have to do something else to make that run in parallel?
So essentially there's another set of collections which are parallel collections, which essentially work with splits and joins. So they split the collections repeatedly into smaller collections until the chunk size is adaptive. So it uses adaptive chunking with the work speeding scheduler to get the chunk size right, and then it rejoins them. So it's essentially a standard state-of-the-art way to do these parallel collections. And I think the new part here is that in other languages you might have a single collection which is parallel, like pararray, Duck-Lee's pararray in Java. So this is a framework. This you can just drop in, you can do anything with that. And you can reuse all the stuff you know from sequential, and it would just work the same way in parallel. That's I think, the big deal about it.
All I need to do is add that split stop par, and there'll be some magic thread pool in the background. Just get into.
There's a thread pool, and you can actually pass the thread pool you want it to use, and if you don't pass a thread pool, it will use a default. Yeah. Okay, so
question is a similar thing. So, does that guarantee parallelism, or is parallelism optional? Because if you have some imperative part of the code which the leaves get to, are you guaranteed that they will run without deadlocking on each other?
They won't deadlock, but you might get beautiful races in that way. Because I mean, the point is, if you run these things in parallel, they will be run in parallel, right? There's no analysis which says, well, actually, you're stepping on it. So, for instance, if you did in parallel a thing that averages out the elements, consecutive elements of an array, let's say, right? And you would run them all in parallel, then you might well get the wrong answer, because you might actually think you have an element of an array, but you actually already got the average. I mean, if you do that by mutating the same array. So there's nothing that prevents you from doing this thing. The way you prevent it from doing this thing is to say, well, actually, I want to do that with immutable collections. So I'm not actually updating the collections that I deal with parallel.
I understand. If you're immutable, if you're fully immutable, everything is easy, but there's not
Right.
a lot of things out in the real world.
If they're mutable, so for instance, pararray is mutable, and then yes, I mean, you just get it in parallel. Essentially, pararray is the same thing as like the pararray for Java. It's essentially the same algorithm, the same efficiency, the same underlying fault joins scheduler.
So there's
Out of
another,
curiosity, did you write it from scratch, or did you start with this code?
We wrote it from scratch.
there's another.
But we measured against this code afterwards. Okay. Another question?
Yes, there's another major source of non-determinism in Java-like languages that you sort of paper over here, and I often paper over it myself, and I'm wondering if you have had a sense of how it impacts here. And the major source of non-determinism here is, and it's even worse than it is in Java code. It's a lengthy preamble. It's object allocation and garbage collection. You don't see it, but it's creating a hell of a lot of objects. And every time you do, and every time you create more objects, you're very likely to incur garbage collection. I've pushed internally in Google immutable data structures everywhere, and I encourage people to use it. But now there's a big Java customer internally who's trying to switch over to using immutable data structure, and it's really having a hard time because of the garbage collection.
Because of garbage collection,
So how do you try to address, what is the way that you would respond to that? Or how do you
Can I interject one thing, which is it's not just performance. This is actually something I use in integral collection occasionally, but you can observe different results, based on, let us say, different hash codes, because of garbage collection.
Yeah. Oh, because of dynamic allocation.
Dynamic allocation and the fact that the hash code, if you don't override object with hash code, is a function of exactly when the object gets allocated.
Yeah. Right. So let me address the performance problem first. So I agree. So performance, I mean, you create a lot of immutable objects, and your garbage collector has to keep up with it. Maybe something that mitigates that is that actually in Scala, if you have collections over primitive types, what you will be able to do, what the mechanisms is there, to actually have them specialized so that you won't box the primitive types in these things. In function values, it's the same thing. So that helps. But on the other hand, if you have collections of strings, so these are heap allocated, and there's nothing you can do. In terms of the hash codes, again, I think the answer is, I guess you should probably discourage inheriting just the hash code from object. That's probably not a good way to do it. You should just calculate them out of the structure, which is what, if you use case classes in Scala, the compiler actually does for you.
Yeah, there are obviously families of classes for which it's appropriate, and others for which it isn't.
I agree.
Has Scala implemented any of the sort of caveat-like mechanisms that a lot of functional programming languages have to try to optimize away object creation in certain cases?
Currently, no. We just rely on essentially escape analysis in the JVMs, which has gotten pretty good recently. So in later ones, we find there's a lot of improvement. Maybe you see something else for your.
Well, they turned it on and they turned it off again.
But now it's on. After 6.1.6.21 or so, it's on.
I'll check again.
Okay, yeah. Okay.
In functional compilers, there's a lot of effort going into analysis for deforestation to avoid the creation of the intermediate data structures. Are you looking at that for Scala?
Well, we're looking at it in a more fundamental context. What we do actually with the Stanford guys who are not far from here, with Kunle Olukutun and Pachandra, we have a very big project that looks at so-called language virtualization, which means that you write this stuff here, and essentially in these collections, what this collection here does to say, how did it turn parallel? Basically, it says, well, my first generator here became from it was a sequential collection, now it's a parallel collection. So the whole thing rests on the type of the generators here. So you, and essentially that syntax is very, very general. So you can have another type of generator that means that instead of executing anything, it just constructs a representation of itself, which essentially this thing does. And then at runtime, you would actually optimize this thing. So what we do is essentially to say, well, to take this to the next level, when you say, well, these parallel collections, they're probably good as long as you have maybe 10 cores or 20 cores or something like that. 24,000 cores, even that is not good enough, right? 24,000 threads. So then I believe you need this next level, which says, well, you really need introspection and compilers that look at the code. And deforestation is one fairly trivial part of that, but there are many, many other things that you have to do there. Yeah.
So in terms of the functional programming, there are certain kinds of applications that I just can't figure out how to write in a functional style. And two examples that come to mind is some sort of interactive editor for structured drawings, and the second one is like games like World of Warcraft or Quake, where you have a large data set where any given player can only affect a small number of variables for each turn, and so you're only mutating a small part of the world, and it's too expensive to process the entire virtual world every video frame, right? And so you want to be able to patch changes to the world. I can't figure out how to do that functionally.
Well, maybe you should just use imperative. So Scala is not a pure functional language. You can perfectly well use imperative code in Scala. You can write it just as you could Java code. But the point is, where you can do it functionally, I believe you should. I think there are more and more reasons why you should. And so sort of this sort of thing is a clear thing that you say, well, yes, of course I could do it with single updates and collections, modifying collections. But that way it's both clearer and more parallelizable. So I think you should. But not. I fully agree that there are some applications where it's just not very suitable, and then you shouldn't use it. Yeah.
So will you permit me to bring up the elephant in the room? Okay.
What is the elephant? So
I think the most important and the most controversial sentence that you said in your whole talk was, once you get the hang of it, it's really, really simple. And I'm quoting word for word. The first place I read that about this, a language with this sort of intrinsic complexity, was Structure and Interpretation of Computer Programming. He pretty much says the same thing. That book is 25 years old or something like that. And I've also found that if you get an former MIT undergraduate drunk and talk to him, he'll tell you, I didn't really understand that class in my freshman year. I loved that book when I went back and reread it when I was a junior. So I'm skeptical that without you to teach them or someone of your caliber, the masses will understand the key core concepts of Scala.
So maybe two arguments. So the first one is
he's offering training.
I wasn't teaching MIT students. I was teaching really pretty run-of-the-mill Java programs.
And I'm saying even MIT students, when you get them drunk, admit. I probably shouldn't be talking about these things, but anyway, admit that when they were freshmen, and admittedly, this was many years ago, and things have changed, had a hard time with these concepts.
But I'm advocating neither scheme nor structure and interpretation of computer programming, even though I must say it's a very fine book. I really like the book, but I'm not advocating it as for general consumption, not at all. But these are really standard Java programmers, not particularly, they didn't seem particularly different from the ones you find. And they didn't have a problem with it. And maybe it's me teaching them, and then I guess we have to teach many more teachers that can do it the same thing, but I think fundamentally, no, it's not hard. It's not hard to do that.
Just with that, something following your stuff is in the last year and a half, I've seen more and more books that help a lot. Because the first time I ran into Scala, I was reading the online documentation 3 years ago, and I gave up after 2 weeks. And 2 years ago, I ran into a couple of bugs, and that would take off. I could do it myself, and I didn't have to do anything special.
Yeah, I'm not debating that you know, anyone in this room couldn't learn it and learn it quickly. I'm wondering if it scales up, you know, to the literally millions of programmers.
That's
who
a
use
good
mainstream
point.
language like
Okay,
Java.
maybe I should quickly go to the end, and then
Sorry about
because
that.
I have a
Shut
slide
up.
that, so I have to drop a lot of the more technical stuff because we're out of time.
Sequel talk. I'll do another talk.
Okay. But I think that slide sums it up that you said Scala feels radically different for producers and consumers of those libraries. So for the consumer, I maintain it's really typically, if the libraries are done well, it's really easy. It works intuitively, and you can concentrate on the domain, not implementation. As an extreme case, I have the case of Kojo. Kojo is essentially a learning environment to learn programming, written in Scala, using Scala as the teaching language, being used by hundreds of girls in an Indian school for disadvantaged children. And it's a beautiful environment that works with, it's essentially built on NetBeans, and essentially it uses Scala as sort of a logo-like subset of Scala.
So I
But it
would
doesn't
love
prevent
to
them to
believe
be-
this argument, and I in fact made this argument, I'm going to say 6-7 years ago, about a bunch of the Java 5 changes, and regrettably, you know, after the world has fought with these things for years, I've come to believe that I was dead wrong. You know, when someone, not no names, added wildcards to your type system, you know, the claim was, yeah, library writers will have to deal with this, but they'll be invisible to users of those libraries, and that turned out not to be true in spades.
No. But I remember the very same time when it was writing mails after mails and after mails and said, don't do wildcards because users will see this stuff. It will be in the face of users, and you should do it the way Scala does it, because in Scala it really is bottled in the library. It was precisely my argument. It was precisely my argument to say wildcards push complexity into the user's hands, and they do. You're absolutely right.
So you still believe that it is possible to isolate the complexity to the library writers, and that Scala has achieved in doing it?
I think we're on a good way to do it. I think if you know what to use, then yes. So there are, believe me, there are a growing number of libraries that are really a pleasure to use and that are extremely simple to use, much simpler than the alternatives. The one question that I have right now is essentially how do we bottle it up? How do we prevent a casual user of a library to do all the advanced stuff that you have to do, all the advanced tools that you have to do that? And my current answer to that is probably profiles or lint-like things to say, well, there would be some things where you would get a warning if you, let's say, use an implicit or things like that. There would be user categories to say, well, a big beginning Scala user should never define an implicit. Just shouldn't, right? Implicits are brilliant, amazingly, because essentially implicits are the key why we could have a sane implementations of arrays in Scala, not like the mess that's in Java. Without implicits, it would have been impossible. So you bring them out of my hands over my dead body, really. I need implicits. But I fully agree, a casual user shouldn't use that. And our challenge now is to really be able to distinguish clearly between one and the other. So I think profiles is probably the way to get there. Right now, it's just essentially good taste and good advice.
Yeah. So you were talking earlier about building cathedrals. Now, if you're going to build a cathedral, you can't just have everyone working in parallel. You need as many workers as possible to build the walls, and then when you've got enough up to there, some can often build the roofs, some can often build the gargoyles, and so forth. How does Scala handle these sort of complicated pipelines where you've got your one task must be partly complete, and then two other tasks depend on that first task, and then a fourth task that depends on all three tasks finally finishing?
I think it falls out automatically from the functional approach. You just say essentially a roof needs the walls to be built on. So essentially you have to pass you pass the walls to the roof builder. So
is the thread pool that handles your parallelization going to ensure that resources are correctly allocated so that you've got as many threads as possible in the first task, and then some threads will go off and do some of the other tasks? Or does that need manual intervention on behalf of the application designer?
I think we need probably more experience to find out, but it's certainly something that with tuning we'll get there. Yeah, but we haven't. I mean, this whole thing, I should say, is in Scala 2.9. It's not released yet, so right now we have the basic implementations. Will be released in probably January as the first RC, and only then people will build bigger applications, and then we will find out essentially what we need to do to make this work over bigger applications. But it's a bit of a glimpse to the future, really, also future for Scala.
Also, there's library work going on right now in both in JDK7, there's something called Phaser, and in other languages as well that tries to make it easier to create such things, so where you have multiple phases of work and you have your parallelism during a certain phase, and then everyone rendezvous and then they go on to the next phase. And there are some languages like X10 and Habanero are both Java-like languages that try to have syntactic support for that kind of thing.
Okay. Were you in any way restricted by your choice to use Java VM in the design of language? Would you have done something different if you would come up with your own VM?
Yeah, but I probably would have had full territorial elimination, which we don't have because of the Java VM. It's just impossible to do it with full interoperability. It's not just the VM, but also the fact that we need to really have a very transparent interoperability with Java programs. That, in a sense, was the harder restriction. Because there are ways to actually, for instance, do territorial elimination reasonably efficiently, but it means that you have to fiddle with the interfaces of all your methods. So essentially, you give them a trampoline parameter. We have a paper on that a long time ago. But it means that essentially your Java methods can't really reasonably call your Scala methods anymore. So we didn't want to do that. Otherwise, I mean, there's some things that are a bit unfortunate, like that every class gets a full thread constant pool and it's a separate file, that there's no useful notion of mixing composition. I mean, even the defender methods that have been proposed for Java 8 that don't quite cut it for what we need. But I mean, overall, I mean, let's face it, it has been extremely beneficial because the kind of optimizations that are done in JVM are to a large degree exactly the optimizations we need to let this run fast. So. Okay.
Maybe outside the